Picture asking your friends for advice on a big decision. You don't weigh every opinion equally, right? One friend really gets you, so their view counts more, and another you politely nod at and quietly set aside. Now, here's the thing. A plain graph convolutional network can't make that distinction at all. It averages all of a node's neighbors the same way every single time, no matter how relevant each one is. The Graph Attention Network from Velickovic and colleagues in 2017 fixes exactly that. It lets each node learn how much to listen to each neighbor. Let's see how it pulls that off. Here's the shift side by side. GCN averages every neighbor equally. The weighting is fixed in advance by the graph structure, essentially just how many connections each node happens to have. Whether a neighbor is deeply relevant or barely matters at all, it still gets the same say in the update. Simple and stable, but honestly kind of blunt. GAT lets the model learn how much to weigh each neighbor. Some connections carry far more signal than others, and now the network can actually say so. The weighting depends on the features involved, not just the shape of the graph. So, two nodes with the same number of links can still treat their neighbors completely differently. Now walk through one attention layer, following a single node as it updates. For moves, take it from raw neighbors to a sharpened representation. First, the node looks out at each of its neighbors. It's about to decide, for every connection, how relevant that neighbor is right now, rather than treating them as an undifferentiated crowd the way a plain average would. Then, for each neighbor, a small learned function reads the two nodes' features together and produces an attention score. Think of it as a relevance rating, computed fresh from the data, saying how much this particular neighbor should matter for this particular node right now. Those raw scores pass through a softmax, which turns them into clean weights that add up to 1 across all the neighbors. Now, every connection has a proper share of attention, sharpened toward the ones that scored high. Finally, the node takes a weighted sum of its neighbors' features using those attention weights. That weighted blend becomes its updated representation, leaning toward the neighbors it judged most relevant and quietly discounting the rest, instead of settling for a flat average of everyone. So what should stick? 3 ideas carry this layer. First, attention weights are learned per neighbor. Rather than a fixed rule baked into the graph, the model figures out relevance from the features, and it can adjust that judgment as it trains on your data. Second, it's a weighted sum, not a plain average. That one change makes the layer far more expressive, because it can emphasize the connections that carry real signal and quietly discount the ones that are just noise. The graph tells you who's connected, but attention tells you who's actually worth hearing. Third, robustness and reach. GAD usually runs several attention computations in parallel, called heads, and combines them for stability, so no single noisy pattern dominates. And because the weighting comes purely from features, the same layer works on brand new nodes it never saw during training. All right, let's lock in the takeaways worth keeping. GET, from Velickovic and colleagues in 2017, upgrades the GCN by letting a node decide how much to listen to each neighbor. It computes an attention score for every neighbor from their features, softmaxes those into weights, then takes a weighted sum instead of plain average. Because those weights depend on the data rather than on fixed structure, the layer becomes more expressive and even works on nodes it never saw in training. Running several attention heads in parallel adds stability, and it's now one of the most widely used graph layers anywhere. If ideas like this finally click when they're explained clearly, Standarity.com has plenty more of them waiting for you. Meet you there.